Hey everybody, welcome to our first online digital learning seminar. Today we're going to be talking about polar versus non-polar molecules. So as we go through today's lesson, you're going to need the following materials. You're going to need a pen or a pencil to take notes. You'll need a printed copy of the Polarity notes that have been uploaded on Canvas, or a blank piece of paper if you don't have access to a printer. The key thing is you have a way of taking notes. You'll also need your chemistry notebook to put the notes in at the end of the lesson. So by the end of today's lesson, you should be able to use electronegativity trends to classify bonds as either polar or nonpolar. You should also be able to draw dipole arrows on a Lewis structure to classify an element in a bond as either dipole positive or dipole negative. And we're going to talk about what those words mean. So when I say we're going to talk about polarity, usually the first thing people think of are polar bears. Sadly, we're not talking about polar bears, but there are some cute polar bear cartoons that I'll try to throw in. Instead, we're going to look at two different types of molecules that are classified as either polar or nonpolar. So before we get started, let me show you a real-world example. So let's say, and I really hope that this does not actually happen, but let's say that somehow you end up with COVID-19 and are coughing. So you cough into your hand, which you're not supposed to do. Please cough into your elbow, but you're sick, so you don't realize it. So you cough into your hand. So I filled this spray bottle with cooking oil and food coloring, and it looks disgustingly like real mucus. So I've I've coughed into my hand. Ew, like if you can see this, ew. And then I'm like, okay, well I need to get rid of this. So I'm gonna dip this in some water, which I just happen to have here, to get rid of it. And I'm gonna rinse this off with water. Well, here's my hand after, quote unquote, getting rid of it. And I'm going to try to not ruin my outfit as I do this. But as you can see, there's still a lot of oil, aka the virus. It may look like it's gone, but it's still there. And let's say that I rub my hands like this, you know, I'm trying to get it off, but I just used water. Ugh. Well, now my hands are covered in oil, aka the virus. Turns out this virus isn't going anywhere, even though I rinsed it off with water. So why is that? So it turns out that water is made up of polar molecules. And the virus, which is actually the case, is made up of nonpolar molecules. So the only way to actually get rid of this is soap. But how does that work? So hold on to this thought throughout the lesson, and at the end we're going to come back to it. So the big question is, what makes a polar molecule, well, polar? So in order to discuss this, we're going to have to think back to our trends unit when we talked about electronegativity. Do you remember what electronegativity is? So electronegativity is defined as the ability of an atom to attract electrons. In other words, how badly does that electron want to be with that atom? The more electronegative it is, the more the electron wants to bond with the atom. So fluorine is the most electronegative element, which means that the closer the element is to fluorine, the more electronegative that element is. So if you were to go online and watch some other YouTube tutorial videos, which isn't a bad idea, and I've posted some links in Canvas if you'd like some more supplemental resources, you may see them calculating the electronegativity difference between two different atoms. You can use the electronegativity difference to figure out what type of bond it is. For instance, if you were trying to find the difference between, let's say, carbon, and fluorine, then you can do 4.0 minus 2.5 because fluorine over here is 4.0 and carbon is 2.5. So if you found the difference between them, which is 1.5, you can figure out what type of bond it is. For instance, anything between 0.5 and 1.6 is considered to be a polar bond. So while that's one way to determine the type of bond, there's another way to do this that does not require any numbers. In order to do this, we need to make sure we understand what a polar bond is, though. So first of all, polar bonds and nonpolar bonds only occur between nonmetals. This means that it is a molecular covalent bond, because if you remember when we studied molecular covalent bonds, those are between multiple nonmetals, whereas an ionic bond is between a metal and a nonmetal. So the first thing that we want to check is make sure that these are both nonmetals and that it is in fact a covalent or molecular bond. So what we're going to do is in a polar covalent bond, the electrons are unevenly shared. So the more electronegative atom is better at attracting bonding electrons, which means that it has a partial negative charge. For instance, in this case, chlorine is more electronegative than hydrogen, so it has a partial negative charge. And this is indicated by this lowercase delta and a negative sign to show that it's partially negative. This lowercase symbol represents dipole. So think pole like positive, negative poles. So this is partially negative. The electrons are going more towards it because it's more electronegative. The other end of the polar bond is the less electronegative atom. So in that case, this would be hydrogen. Its bonding electrons are being pulled away from it towards the chlorine, so it has this partial positive charge. This is indicated by the same symbol, this lowercase delta, but now it has a plus sign to show that it's partially positive, has less electrons. So if you were to see these two signs, that should mean that chlorine is hogging most of the electrons, just like how this picture, if we were to go back, shows. Chlorine is hogging the electrons, so chlorine is the dipole negative, whereas hydrogen is that dipole positive. So going back to what we said before, polar and nonpolar bonds only occur between nonmetals. So it means that if it's between two nonmetals, it has to be a molecular or covalent bond. So only after you've discovered and established that it's molecular covalent, you need to ask yourself the following two questions. If I can find it. So, is it between carbon and hydrogen? And then, is it diatomic? If it's diatomic, it means that it's two of the same element. So for instance, over here, I have two hydrogens, hydrogen, hydrogen. This means that it's diatomic. It's two of the same ones. Carbon-hydrogen is just literally, is it a bond between carbon and hydrogen? So if you answered yes to either of those two, then it is nonpolar covalent. Otherwise, if you answered no to both of these, it is a polar bond for sure. So let's say that you're dealing with a polar bond. For instance, let's use hydrogen and fluorine. So let's say that I was dealing with hydrogen and fluorine. Still adjusting to this digital learning thing. So if I were to do this, I need to make sure that it's polar. So first of all, these are between two nonmetals, hydrogen and fluorine, both nonmetals. So it is molecular. Is it between carbon and hydrogen? No. Is it diatomic? Meaning, is it two of the same element? No, there's one hydrogen, one fluorine, not the same element. So I'm going to quickly draw the Lewis structure. Remember that I don't need any lone pairs around hydrogen because hydrogen only needs 2 electrons, which is represented by that bond, but fluorine needs 6 more. So I'm going to draw the lone pairs around fluorine over here. So this is definitely a polar bond. So I'm going to use arrows to point towards the partial negative end, aka the more electronegative end. So I'm going to draw my dipole arrow, which goes here. Because fluorine is more electronegative. It is actually the most electronegative. The plus side of this arrow, notice how it does look like a plus sign, shows the partial positive end of the bond. And then I also need to draw this dipole positive and this dipole negative as well, just to show that fluorine is getting more of the electrons than hydrogen. Imagine like siblings. They're still sharing, sort of, but one sibling is hogging more of your toys or your stuff than the other sibling. So let's pause for a few minutes and review everything we've covered so far. If you're using the notes that were posted on Canvas, this is a table that you're filling in the notes. So remember that there are 3 types of bonds. There's nonpolar, which is covalent. There's polar, which is covalent. And then there's ionic. And if we were to think about the types of elements in the bond, well, it's right here in the word covalent molecular. That means that's only nonmetals. Only nonmetals. But ionic, like last unit we talked about ionic, it's made up of metals and nonmetals. So if you see a metal, stop, it's ionic, you don't need to go any further. In terms of sharing electrons, if it's nonpolar covalent, that's perfect sharing, everyone's happy, totally equal. If it's polar covalent, well, they're still sharing electrons, but unequally. One element is hogging the electrons more than the other. But ionic, they don't even bother sharing. There's just stealing electrons and transferring and getting rid of them. They don't bond at all. In terms of the difference in electronegativity, so if you were to go back and use the method I showed you in which I calculated the difference, anything between 0.0 or 0.4 means that it's nonpolar covalent. That means that is such a small difference that there's basically equal sharing. And since they're equally sharing, there's absolutely no charges. Everyone's happy. If it's polar covalent, it's going to be between 0.5 and 1.6. And we use partial charges to show that, well, one is partially negative. They're still sharing, so it's not completely negative or positive, but one is hogging the electrons more, which is negative, and one has fewer electrons towards it, which is partially positive. But then ionic is anything between 1.7, and they've got complete full charges because they've completely transferred and stolen electrons. Here's another visual representation. So if you were to look at nonpolar covalent, it's totally equal. A and B are even. Polar covalent, well, B is clearly hogging more electrons than A. And ionic, they're not even sharing. It's just positive and negative. So just a quick check. If a compound is polar, which of the following is true about the electrons? They are shared totally equally, they're shared unequally, or they're totally completely transferred. So which one most closely matches this? I'll give you a hint, the answer is not D. So the answer for polar is B. They are shared slightly unequal. It's this unequal sharing. One is hogging more than the other. They're still sharing, it's just unequal. Let's try another one. If a compound is nonpolar, which of the following is true about its electrons? A, they are shared equally. B, they are shared slightly unequally. C, they are completely transferred. Or D, none of the above. Please don't pick D. So the answer for this one is A. So the last thing I want to have you guys do is to complete this table. Try to do it on your own first before continuing and watching to check your answers. If you're completely not sure, please check out the other resources that I've posted on Canvas, and then continue going through this. So pause while you do this and then restart. Okay, hopefully you guys have completed the table at this point. So if we were to look at fluorine and fluorine, and we wanted to know what type of bond it is, ionic, polar, or nonpolar. The first question is it a carbon? First of all, is it metal and nonmetal or two nonmetals? So fluorine is nonmetal, and there's two of them. So nonmetal, nonmetal. So it has to be either polar or nonpolar. So then the next question is it a carbon-hydrogen bond? No. Is it diatomic? And the answer is yes. It is two of the exact same elements, fluorine and fluorine. So this means that it is diatomic. In other words, we can write it out as F2, diatomic. So that means that it is a nonpolar covalent bond. So I'm going to write nonpolar. Since it's nonpolar, that means that they are equal sharing, everyone's happy, so they have zero charge. Now let's take a look at the next one, H and F. Again, two nonmetals, which means it has to be polar or nonpolar. It's not a carbon-hydrogen bond, but it's also not diatomic, which means that this has to be a polar bond. And if it's polar bonds, it's unequal sharing, which means that it's a dipole positive and a dipole negative. And finally, the last one. Well, if you were to look at sodium, sodium's a metal on the periodic table. So stop everything. It's ionic. We do not need to go any further. So we are dealing with an ionic bond here, which means that the electrons are being completely transferred. Since they're being completely transferred, you're going to have a full positive and a full negative charge. So take a moment now, go through the resources on Canvas, and begin working on the polar-nonpolar bond worksheets. When you feel like you have a mastery of this skill, come back and we're going to go over part 2 of the lesson. Thanks for hanging in there, guys. Please reach out if you have any questions. Remember that my office hours are every day from 10 to 11 and 2 to 3 for chemistry. Happy studying! Hey everybody. So before we move on, I want you to ask yourselves the following 3 questions. Do you know how to draw Lewis structures of an atom? Can you determine if a bond is polar or nonpolar? And then based off that, can you draw dipole arrows if it's polar? If you answered yes to all 3 of these things, then you're ready to move on. If you answered no to any of them, please go back to the Canvas site and revisit some tutorials and worksheets so that you become proficient on these 3 things. So for this next section, we're going to take polar bonds and we're going to one-up it. Now we're going to talk about polar molecules. These are 2 different things. A polar bond does not necessarily mean that it is a polar molecule. So by the end of this lesson, you should be able to draw Lewis structures with dipole arrows to determine if a molecule is polar or nonpolar. You should also be able to take the example that we were doing at the beginning with the coronavirus and describe what makes soap unique using polarity. So if we determine a bond in a molecule is polar, then the next step is to determine whether or not the molecule itself is polar. So whether a molecule is polar or not determines a lot of its properties. Remember what I said before. It is possible to have a polar bond, but the molecule itself be nonpolar. These are 2 very, very, very important statements, and so I need you to pause this video and write these down. If a molecule has only nonpolar bonds, then it will always be a nonpolar molecule. But if a molecule has polar bonds, it can either be a polar or nonpolar molecule depending on 2 things. So these are the 2 questions you need to ask yourself this unit. Is there more than one polar arrow? If there's only one polar dipole arrow, it is a polar molecule. If there is more than one arrow, then you need to ask yourself question number 2. Are there lone pairs on your central atom? Remember, lone pairs, I mean like the little dots, the electrons around the central atom. So if there are electrons around the central atom, then it's a polar molecule. But if there's not, if there are only bonds, no dots, then it's nonpolar. So the first step to figuring out polar molecules is to always draw the Lewis structure of that compound. Okay, for the first example, I'm going to do hydrogen monochloride, HCl. So I'm going to start by drawing my Lewis structure. Remember the NAS method. N stands for need, A is for available, and S is for shared. So I'm going to start with N. Remember, every element except for hydrogen needs 8 electrons. Hydrogen only needs 2 to be happy. So in this case, I'm dealing with hydrogen, so it needs 2, and I have 1 hydrogen. I'm also dealing with chlorine, and chlorine needs 8 because it's not hydrogen, and I have 1 chlorine. So 2 plus 8 gives me 10 electrons. But available is the number of valence electrons. So I'm going to look on the periodic table. Hydrogen is in group 1A, so that means that I have 1 valence electron and 1 hydrogen. And chlorine is in group 7A, which means that I have 7 valence electrons and 1 chlorine. So 1 plus 7, that gives me 8 available electrons. So remember to find shared, I'm going to do N minus A. So 10 minus 8, which is going to give me 2 shared electrons. Remember that every bond is equal to 2 electrons. So to find the number of bonds, I'm going to divide the number shared by 2. So I'm going to end up with 1 bond. So now it's time to draw it out. Remember, this is Cl, not carbon and iodine. So hydrogen monochloride. So I have a hydrogen and I have a chlorine. So now I'm going to connect these with 1 bond, and oh look, all I needed was 1 bond. I don't need to double up on anything. So now let's ask ourselves the following question. Is hydrogen happy? Well, hydrogen has 1 bond connecting to it. And remember that 1 bond is equal to 2 electrons. And oh, that's all hydrogen needs to be happy is 2 electrons. So hydrogen's good. Chlorine also has 1 bond connecting to it, so that's 2 electrons. But chlorine needs 8 electrons, so it already has 2. Now I'm going to draw 6 more around it so that it has 8 electrons. So now chlorine has 8 and hydrogen has 2. Now I can double check my work. I know that 1 bond is 2 electrons, so 2, 4, 6, 8, and that's how many are available, so I'm good. So now the next step is to check and see if it is a polar bond. Well, this is not a bond between carbon and hydrogen, and it's not diatomic because these aren't the same elements connected. So it's polar. So I can draw my polar arrow going towards chlorine because chlorine is the more electronegative one. I'm going to do my dipole symbols. And now I'm going to ask myself the following questions to determine if it's a polar or nonpolar molecule. So are there multiple polar arrows? Well, the answer is no. So automatically it's going to be a polar molecule because there are not multiple. There's only 1 dipole polar arrow. If we were to ask ourselves the second question, does the central atom have lone pairs? Well, there is no central atom. So we are good. Okay, moving on to the next slide. Carbon dioxide. So carbon, we're going to set up our NAS. So once again, carbon needs 8 electrons, and there's 1 of them. Oxygen also needs 8 because it's not hydrogen, and there's 2 of them. So 16 plus 8 gives me 24. Available is, for carbon, it's found in group 4A, which means that carbon has 4 valence electrons, and again, there's 1 carbon. And then oxygen is found in group 6A, so there's 6 valence electrons, and there's 2 of them. So 12 plus 4 gives me 16. So I'm going to do 24 minus 16, which is going to give me 8 shared electrons. Well, if there's 8 shared electrons, that means that there's going to be 4 bonds. because remember, one bond is equal to 2 electrons. So now let's draw it out. Remember, I put the least common element in the center. In this case, that's carbon. And as a rule of thumb, carbon always goes in the middle. So now I'm going to surround it with these oxygens. And I'm going to start by connecting it with one bond. Well, so I have 2 bonds, but I need 4. So now I can go back and I can double up. 3, 4. So now I have 4 bonds. So now let's check and see what's happy and what needs more lone pairs. So if we look at carbon, carbon has 1, 2, 3, 4 bonds around it. That means that carbon has 8 electrons around it. So carbon is feeling pretty good because it needed 8 electrons. This oxygen only has 1, 2 bonds connecting to it, which means that it has 4 electrons. It needs 4 more in order to have 8. So I'm going to draw 4 more electrons so that it also has 8. And I'm going to do that on both sides. 1, 2, 3, 4. So now let's check and see. These are all happy. Now let's make sure that it adds up to 16. So if I have 2, 4, 6, 8, 10, 12, 14, 16. And so it adds up to 16. We're good. So now the next step is check and see if these are polar or nonpolar bonds. Well, first of all, you may see O2 and think, oh, it's diatomic, it's nonpolar, but the oxygens are not bonded to each other, which means it's actually not diatomic. We're looking at the bonds between carbon and oxygen. So this is not a bond between carbon and hydrogen, and the bond between carbon and oxygen is not diatomic. These oxygens are not connected together. It's carbon and oxygen, so it's not diatomic, which means it is a polar molecule. In this case, oxygen is more electronegative than carbon, so the dipole arrows are going to go towards the oxygens. And I have 2 dipole arrows going towards each oxygen. So now let's look at the following questions. Are there multiple polar arrows? The answer is yes. Does the central atom have lone pairs? Carbon is the central atom. Does it have electrons around it in terms of dots? And the answer is no. And since it does not have lone pairs, this is a nonpolar molecule. Because the way this works is the dipole arrows are basically canceling each other out, which makes the molecule itself nonpolar even though there are polar bonds. Let's take a look at another example. Feel free, if you're getting the hang of this, to pause and check this yourself and then follow along to see if you're correct. So I'm going to do NH3, which is ammonia. So once again, I'm going to set up my NAS. Nitrogen needs 8 electrons, and there's 1 of them. And remember, hydrogen's my one exception, and it only needs 2. And there's 3 of them. So 8 plus 6 is going to give me 14. I need 14 electrons, but nitrogen, which is found in group 5A, only has 5 valence electrons, and there's 1 nitrogen. Hydrogen is found in group 1A, so there's 1 valence electron, and there's 3 of them. So 5 plus 3 gives me 8. So to find my shared, I'm going to do 14 minus 8, which gives me 6 shared electrons. Remember, I divide that by 2 to find the number of bonds, so I have 3 bonds. So now let's draw it out. Nitrogen is my least common. There's only 1 of them, so nitrogen's going to go in the middle, and the hydrogens are going to go around it. So now I'm going to start by connecting each one with a single bond. And that's 1, 2, 3, and that's all I needed was 3 bonds. So I do not need to double up on anything. Now let's check and see if the elements are happy. Hydrogen has 1 bond connecting to it, and 1 bond is equal to 2 electrons. Well, that's all hydrogen needs is 2 electrons. So hydrogen is good. Each of these have 2 electrons, so it's good. It does not need any more. Nitrogen has 1, 2, 3 bonds around it. So that adds up to 6 electrons because each bond is 2 electrons. So 2, 4, 6. But how many does nitrogen need to be happy? It needs 8. So I'm going to add 2 more dots on the bottom here in order to get to 8. So now I can check my work by saying 2, 4, 6, 8. And that's what I needed, so I'm good. So now let's check and see if it's a polar bond. The bonds between nitrogen and hydrogen is not a carbon bond, not a carbon-hydrogen bond, and it's not diatomic because it's between nitrogen and hydrogen. So that is a polar bond. Nitrogen is more electronegative than hydrogen, so the dipole arrows are going to go towards nitrogen. And each one is going to have a dipole arrow because each bond contains a dipole arrow. Each hydrogen is dipole positive. So I'm going to go back and label these dipole positive, dipole positive, dipole positive. So now that I know it's polar bonds, I'm going to ask myself the following questions. Are there multiple polar arrows? The answer is yes. Does the central atom, which is nitrogen, have lone pairs? Well, the answer is yes, it does. It has 2 electrons by itself around it. So, because of these lone pairs, this is a polar molecule. If there were no lone pairs, because there were multiple dipole arrows, it would be nonpolar, but these lone pairs here make it a polar molecule. So I'm going to do another example. Once again, feel free to pause if you've got the hang of this. So I'm going to do carbon tetrachloride, and so I'm going to go through, set up my NAS. At this point, I'm going to go a little bit quicker. Carbon needs 8 to be happy, and there's 1. Chlorine needs 8 to be happy, and there's 4. 32 plus 8 gives me 40 electrons. Wow, that's a lot. Carbon is found in group 4A, so I have 4 valence electrons, and chlorine is in group 7A. And there's 4 of these. If you don't know these off the top of your head, which you're not expected to, check your periodic table. So now 28 plus 4, well, that gives me 32. So 40 minus 32 gives me 8 shared electrons. That means that I'm going to have 4 bonds. Carbon is my least common element, so it goes in the middle, and I'm going to put chlorines all around it. Once again, connect these with single bonds first. Each one is connected by a single bond, and I've got 1, 2, 3, 4, which is perfect because I do not need to double up. So now we're going to check and see if they're happy. Carbon has 1, 2, 3, 4 bonds around it, which means it has 8 electrons. So carbon is good. Chlorine only has 1 bond around it right now. Each chlorine only has 1 bond. Chlorine also needs 8, so it needs 6 more electrons. So I'm going to add 1, 2, 3, 4, 5, 6. And I'm going to do that for each chlorine. And once I've done that, then I can go back and check if it matches my available. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And that's what I needed. So now let's check and see if the bonds between carbon and chlorine are polar or nonpolar. It's not between carbon and hydrogen, and it is not between chlorine and chlorine. It's between carbon and chlorine. So it is a polar bond. So chlorine is dipole negative and carbon is dipole positive. So I'm going to draw my arrows. And then ask myself the following question. Are there multiple polar arrows? The answer is yes. Does the central atom, which is carbon, have lone pairs? There are no dots around carbon itself. Since the answer is no, this is a nonpolar molecule. This is the last example that we're going to do. If you can do this one, then you are in good shape. So I'm going to set up my Lewis structure for this. This time I'm dealing with 3 elements. I'm dealing with carbon, hydrogen, and chlorine. So I'm going to set up my NAS. Carbon needs 8, and there's 1 carbon. Hydrogen needs 2, and there's 3 of them. And then chlorine also needs 8. Every element except for hydrogen needs 8. So 8 plus 6 plus another 8, that gives me 22. So I need 22 electrons. But now I'm going to look at available. Carbon is in group 4A, so there's 4 valence electrons. Hydrogen is in group 1A, so there's 1 valence, and 3 of them. And chlorine is in group 7A, so there's 7 valence. So 7 plus 3 plus 4, that gives me 14. So 22 minus 14 gives me 8 shared electrons. That means that there's going to be 4 bonds. In this case, there's only 1 carbon and 1 chlorine, so this is where we use that rule where carbon always goes in the middle. So I'm going to put carbon in the middle and then surround it by these other ones. 3 hydrogens and a chlorine. It doesn't matter where you put them as long as there are 3 hydrogens and a chlorine surrounding the carbon. And now I'm going to connect these. Connect them 1, 2, 3, 4, and oh look, there are 4 bonds. I do not need to repeat anything. I don't need to double up. So now let's check and see what's happy. Hydrogen has 1 bond connecting to it, which means that it has 2 electrons. So hydrogen is good. Carbon needs 8, and there's 1, 2, 3, 4 bonds surrounding this carbon, so carbon is also good. Chlorine has 1 bond, so that's 2 electrons. It needs 6 more to hit 8, so 1, 2, 3, 4, 5, 6, 7, 8. So now chlorine has 8 as well, and so it's good. Let's double check our available. If I have 2, 4, 6, 8, 10, 12, 14, that checks, so I'm good. Now it's time to see if there are any polar bonds. Well, the bonds between carbon and hydrogen are nonpolar, because remember, this is a carbon-hydrogen bond, so these are nonpolar, but there's also a bond between carbon and chlorine, so this bond is polar. Chlorine is going to be the more electronegative, and carbon is dipole positive. So I'm going to draw my arrows. I'm going to draw it going here. So the arrow is going towards chlorine because it's dipole negative. So now let's answer these questions. Are there multiple polar arrows? Well, no, there's only 1 polar arrow, and that's going towards chlorine. Does the central atom have lone pairs? No, but it doesn't matter. Because there's only 1 dipole arrow, that means that this is a polar molecule. The central atom with lone pairs only applies if there's more than 1 dipole arrow. So going back to our example earlier in this lesson with the coronavirus, the virus is a non-polar molecule, but it's made up of polar bonds. Here's the takeaway. Like molecules dissolve like molecules. So even though it has polar bonds, it's a non-polar molecule, which means that a non-polar molecule is not going to dissolve in a polar molecule like water. Like molecules dissolve like molecules. Polar molecules dissolve in polar, non-polar molecules dissolve in other non-polar. So in this case, water and oil, or the virus, do not mix. Here's something that may help you appreciate like dissolving like. It's the joke of the day. Polar bear, help, help, I'm dissolving. Another bear, but bears are insoluble. Well, that's easy for you to say. You're not polar. Okay, just a little something to help you get through this. Well, here's what makes soap so special. Soap actually has a polar head, but a non-polar tail, which allows it to actually bind both things together, the polar head bonds with a polar molecule like water, where the nonpolar tail bonds with other nonpolar molecules like the virus or oil. And so then because these have bonded and are being held together with soap, that's how we're able to get it off. So soap is really unique, and we're actually going to come back to this phenomena throughout this unit. But it's important to realize that because of polarity, that's what makes soap so effective, allowing it to bind to bacteria, dirt, and water, and to really remove those germs and keep you safe. So now it's time for you to practice. So I want you guys to make sure that you're checking week 1 on Canvas and submit any assignments on there by Wednesday, April 1st at 11:59 p.m. As of right now, the district still has a schedule to return on Wednesday, April 1st. So if we end up having school that day, go ahead and still plan to submit things through Canvas in order to stay consistent. But if for some reason they continue to extend, then make sure that you're checking Canvas for week 2. This is the first day of the lesson, so imagine that this was a Monday, Tuesday lesson. Make sure that you watch part 2 of the class, which is like a Thursday, Friday lesson, where we're going over intermolecular forces. Remember, office hours every day, 10 to 11 and 2 to 3, I believe. Yeah, 10 to 11, 2 to 3. And that is through the Teams app. So make sure that you check the email that I sent, and it is Microsoft Teams. As always, happy studying, guys. Please stay safe. I miss you all. And let me know if you have any questions.